Welcome to this lecture on compile construction. Today we're going to have a look at another static analysis method to help us with optimizations, and this static analysis method is called available expressions. So as the name already says, we're looking at expressions which might have been calculated before, where we already have some intermediate result calculated and stored away somewhere. And if we can reuse this, of course, we can save quite a bit. So today we're looking at data flow analysis considering global properties of expressions and their availability. From this we derive a differentiation between semantic and syntactic analysis and then show how to use available expressions analysis to do optimizations. So when we want to discover global properties of expressions, we look at analysis here that eliminate redundant computations of expressions over the piece of program we are looking at. So programs may contain code whose result is needed, but in which some of the computations we are doing is simply redundant. So we're repeating some computation that has happened before in the execution of our program, so of the very same program we're looking at. So if this has happened before, maybe we won't have to do it again. And this first analysis on this, we'll see another one later on in the next lecture. This first analysis is called available expressions, and this is concerned with replacing an expression by a pre-computed value. So we are again considering program points. So if we are looking at a certain program point, we call it U. Our available expressions analysis discovers those expressions whose results at this program point U, so when we arrived at this program point, are the same as their previously computed values. So we know we have an expression at this program point, and we know we have the same expression at a previous program point in the execution of our program, and we need to make sure that the values of the variables making up these expressions haven't changed in between, so the intermediate result still is the same. And this has to happen regardless of the execution path taken to reach U. So now we have to consider all execution paths that are available to reach our current program point U we're looking at. So let's look at an example here. Any given program contains expressions, obviously, a finite number of expressions because programs are obviously not infinitely long. So these expressions produce values, obviously, and these values might actually be useful later on. So the first thing we are going to look at is the set of all expressions of a program. So for example here, we have three expressions here. So we have x times y, which we assign to z. We have another one, s plus t, which we don't assign to anything which is a variable because we just print it out, but we may have the intermediate result stored in a register or memory location. And then we have a third expression in our little example program here, u divided by v, which we store in w. So our program contains three different expressions, x times y, s plus t, and u divided by v, which is the set of all expressions of our program. So we are now considering availability of expressions. So availability, as the properties we've seen before in static analysis, is a data flow property of a given expression, and availability asks the questions, has this value of the expression we are currently looking at, has this already been computed? So we have given expression x times y, so we need to figure out, are there any other places in our program where x times y has already been calculated? And if this is the case, we need to make sure that x and y still have retained their previous values, no matter how we got from this previous place to here, our current program point. And if we have this intermediate result, well, we can reuse it, obviously. So at each instruction, each expression in our program is either available or it's not available because it has never been calculated before, or values have changed in between. So what we're doing is we are considering availability of an expression from the perspective of a single instruction here. So each instruction, or each node of my control flow graph where I'm considering here, has an associated set of available expressions. So for each instruction, for each CFG node, we can actually figure this out. So For example, if we have our little program from the previous slide here, we have x times y, we have s plus t. The values of x, y, s, and t haven't changed in between. So when we arrive at our instruction n here, we know the available instructions before arriving here are x times y and s plus t. So if you think this is all familiar, yes, you've seen this before from live variable analysis. So expression availability and variable liveness analysis share a number of similarities. So both are rather simple data flow properties. We're not taking a look at more complex ones in the term of this course here, but they do differ in a number of important ways we're going to look at. So the most important way is actually the way these analyses look at the availability. So we are looking at a difference between semantic and syntactic analysis here. So availability differs from previous examples we've been looking at in static analysis in a very subtle way, which is very important. So here we want to know which expressions are definitely available. So there can be no case in which an expression has changed values or stuff like that. We need to know if we arrive at a program point and we have availability, it has to be available there in any case. So we know they have to be computed before at a certain instruction. And previous analysis have actually considered things that might have been available, so may be available, but we're not quite sure if they're available. And so we can define that an expression is semantically available at a node n in our control flow graph here if its value gets computed and, that's important, not subsequently invalidated between then and our node n along every execution sequence ending at that program point. So for example, on the left-hand side, we have int x equals y times z again, and then maybe at the end of a function we want to return y times z. So if y and z don't change in between, we could have simply written return x here instead of return y times z, obviously. So we know this expression would be available if nothing else would have happened in between. Now, here we have something different on the right-hand side. So again, we have int x equals y times z. But in between, we are changing the value of y to be a plus b. So when we have return y times z here again, the value of y has changed in between. So the value we are returning here is in almost any case different from the value we've calculated above. So because we invalidated this variable y, making up our expression up here, we can't just reuse the result we calculated up here. So y is invalidated, which means y times z is unavailable at that location in our program. So an expression is syntactically available at a node n if its value gets computed and not subsequently invalidated along every path from the entry of the control flow graph to this program point n we're looking at. So semantic availability means we're looking at the execution behavior of a program, whereas syntactic availability means we're considering the program's syntactic structure. So we have another example here on the left-hand side. So essentially what we're doing here is we're using two if conditions here. So the first one calculates the expression x plus 1 times x plus 1, so x plus 1 squared obviously, and compares this to y, and if this is equal to y, we assign x plus y to a variable s. And on the other hand, we calculate that one here, and of course you know from your basic mathematics education that the expression here is the same as the expression down here. We're not considering any overflows of variables and something like this at the moment. So now if this expression is not equal to y, we're assigning x plus y to something else, and then after those both if expressions, we are returning x plus y. So semantically, we know either this one is true, so x plus 1 times x plus 1 is equal to y, or that one is true. It's just x plus 1 times x plus 1 written differently. And here we check for inequality. So either we have this assignment here or we have that assignment here. So semantically, we would know x plus y is available, and the recomputation of x plus y is thus redundant because we can reuse either that result or this one here, depending on which path we took through our program. Now, we can also have a closer look at this when going one level deeper. So we're lowering this to an intermediate representation. So what we do here is in the first block of statements here, in our first basic block, we just check our expression here. So x plus 1, let's say we have x, we have 1, and we start in t32. Then we multiply t32 with itself, so we square our value here. And then we compare this intermediate value t33 to y. And if it's equal, we add x and y and start in s. If it's not equal, well, we're evaluating the second if condition here in our basic block. So we're multiplying x with itself. We're multiplying x times 2 here. So we're adding x squared and 2 times x into t36. So we have the first part of our expression here. Then we add the final 1 to it. And then we compare it to y again. And now if it's not equal, we add x and y stored in t. And finally, we would add x and y stored in res1 and return it as result. Now, if we don't consider semantics, but just syntactic analysis, there might be a path where actually both conditions aren't fulfilled. Of course, in our real program, this can't happen, but our compiler needs to be intelligent enough to figure this out. So on our red path, directly through the flow graph, it could, in theory, if we only look at the syntax, happen that neither this nor that expression is actually computed. So syntactically, at this point, our compiler would have to assume x plus y is syntactically unavailable at the last instruction. Of course, this red path never actually occurs during execution due to the fact that these both expressions are actually identical, and we either check for if they're equal to y or not equal to y, and so we either calculate x plus y here or we calculate it up there. So if an expression is deemed to be available, we might be endangered of doing something which is problematic. So something dangerous in an optimization, like we might be convinced to remove an instruction which recomputes its value. In contrast, if we're looking at live variable analysis, we found safety by assuming that more variables were live, and here we're going on the safe side by assuming that fewer expressions are available. So we can look at this in terms of set relationships. So let's say this is the set of all expressions in our program. So of course we have a number of expressions which are simply semantically unavailable at our program point n. These are on the right hand side. These we don't consider anymore. And then we have a number of expressions in that green circle here which are semantically available at n. So the difference between semantic and syntax. And as we've seen before in our example with the 2 if conditions, some of those actually are not syntactically available, because if we only look at syntax and not at the values of variables, so not at the semantics of our execution through our program, we cannot really guarantee that these might actually be evaluated. So essentially, even though the green circle would indicate all useful ones, we are going on the safe side and only take the ones inside of our blue dotted circle here, the ones that are syntactically available at our program point. And this is the so-called imprecision of our analysis. So essentially, we're possibly missing some possibilities for optimizations here by staying on the safe side with the syntactic analysis. So again, we see this is our problematic path here. So we won't actually execute this one and that one here if we only look at syntax and not at the actual values of variables and their comparison. So available expressions is a forward data flow analysis. So we need to know what happened before, so which expressions have been calculated before, and if the values of the variables that make up these expressions has not been changed. So information from past expressions must be propagated forward throughout our program to discover which of the expressions are actually available. So for example, we have a program that contains several expressions consisting of x times y, like that one, this one here, and this one here. And so if we have this final instruction here, int z equals x times y, we need to know if any of these, and if yes, which of these is actually available at that program point. So unlike variable liveness, expression availability flows forward throughout the program. Variable liveness went backward and looked in steps back. But similar to liveness, each instruction, of course, has an effect on the availability information as this data flow information flows past our instruction. So an instruction makes an expression available when it generates or computes its current value. So let's start with no available expressions here. Then we execute print a times b. So we generate a times b. We have an expression that we calculated and which we might want to reuse. So the next instruction we are calculating c equals d plus 1. So we have yet another instruction generated, d plus 1. And the final one here on this slide is e equals f divided by g. So we have yet another one, f divided by g, as part of our available expressions. Now let's continue. So this was the set of available expressions before this program point. The next one calculates a equals 7. So there's no actual expression involving variables on the right-hand side. It's just a constant assignment. So we're not generating anything new here, but we're killing a value. We're killing all the expressions where a is a part of. So if we have a look here, this is the only expression where a is a part of. So we're killing it. It gets removed from the available expressions because we have this intermediate result here. The value of a has changed. So if somewhere down here we wanted to evaluate a times b again, it would have a different value. And again, in the next expression here, c equals 11, we're killing all expressions containing a c. So the first one here. So we're left with these two, and these two contain d and e. So our final instruction here assigns yet another constant to d in this time. So we kill all the expressions containing a d, which are all of them. So we're left with no available expressions after assigning of these three constants here. So we see that is pretty similar to what we've seen before. So as in as in live variable analysis, we can devise functions gen and kill for each program point n, which gives the sets of expressions generated and killed by that instruction at the node n we are just currently looking at. This situation is a bit more complicated here, because an assignment to a variable x just doesn't kill one expression, but in the worst case it kills all expressions in the program which contains an occurrence of that variable x. So it might be 0, it might be a larger number. So we define something new. We define a set of expressions which contain a variable x and call this ex. So we can determine some gen and kill sets here. So gen of the instruction x equals 3 is actually the empty set because it's no expression, it's just a constant assignment. We don't need to store this again because, well, we can just cheaply get this constant again. If we execute x equals 3 and look at the kill set, we kill all the instructions, all the expressions in our available expression set which contain variable x. If we look at print x plus 1, it generates the expression x plus 1 because we have to calculate it in order to print it. And we don't assign anything here, so we're not destroying any previous values, so the kill set is empty. And then we have something else, which is x equals x plus y. So this generates x plus y, obviously, because we are calculating it. But then it also destroys x again, because we're assigning x plus y to x again. So essentially, if we would execute x plus y again after this, it would have a different value. So if we execute x equals x plus y, we are killing all the expressions containing x, including the one we've just generated here. So as availability flows forwards past an instruction, we want to modify this availability information. So we are adding expressions that are generated by this instruction so they become available. We're removing all the instructions which are killed by our instructions, so those become unavailable. So again, if we have y plus 1 before, we're printing x plus 1, we're generating x plus 1, so after this instruction we have x plus 1 and y plus 1. And on the other hand, if we have an instruction x equals 3, we have x plus 1, y plus 1. Before this instruction in our available expressions, we're killing all the ones containing an x. We're just left with y plus 1 afterwards. And as we've seen, if an instruction both generates and kills expressions, like in our x equals x plus y, well, we're generating it, x plus y, and right away we're killing everything that contains an x. So we're throwing it out again. So we have x plus 1 before, x plus 1, well, is not useful here. Anyways, we recalculate x plus y, so we generate something new, and then we kill all the expressions containing an x, so x plus 1 and the recently generated x plus y, so we're again left with y plus 1. So if we consider the in and out available expressions for an instruction n, the sets of instructions which are available immediately before and after a node, we can write it in a shorthand notation using the following equation. So the available expressions at the end of an instruction, so the out available expressions, are the in available expressions. We add to this set the ones generated by this expression, and from this joint set we subtract the ones afterwards, that's important, that are killed. And the order of evaluating this is important for exactly our corner case here, that we're using a variable here which generates a new expression and then killing it right away by assigning it to one of the variables contained in this expression. So using this, we can look at an example of how to calculate this, and this is the way you would do it if you would implement this static analysis in a compiler. So for example, we have again our instruction x equals x plus y as our instruction n here. Before that instruction, we had the in available set of x plus 1, y plus 1, and so now we join the in available with the gen set and subtract the kill set. So we have that one here, x plus 1, y plus 1. We're joining x plus y, and then we immediately kill all the ones containing an x, so x plus 1, x plus y again, and of course we're left with y plus 1. Okay, so it's not that difficult as you see, and it's rather straightforward to implement in a compiler, considering you have the right parts of information provided in your intermediate representation of your instructions or basic blocks you're looking at. So the more complex problem actually arrives when we look at control flow joins. So when a node in our program has a single predecessor, as we've seen before, it's simple. So the in available information, so the in available expressions of the current node, are the out available expressions of the previous node. Now when a node has multiple predecessors, like in our example with an if and an else maybe, so either we come from a left-hand side and arrive at an instruction, or we come from the right-hand side here and arrive at the very same instruction, then we have to consider both sides. So when a node has multiple predecessors, the expressions available at the entry of that node are exactly those expressions, that are available at both paths or in all paths of the predecessors here. Because we have to make sure that the expression we're maybe optimizing for was calculated here as well as here before we're able to reuse it somewhere. So that's the big difference to live variable analysis. We need to figure out and we need to make sure that all of the predecessors of such an instruction, which is at the join of a control flow, have calculated the expression. And in live variable analysis, only the condition that one or any of the successors has actually calculated this expression before. So essentially, we can go through this again. So here we have a sequential control flow. So here we have the outset x plus 5, which is of course the inset of our instruction m here. So m calculates z equals x times y. So we have x plus 5 and x times y available, because we're not destroying x here. On the right-hand side, we have y minus 7 as the outset, which becomes the inset of our instruction n here. We're just printing it, so we're not killing anything here. So we have x times y and y minus 7 available. And now, if we join the control flows, we need to have the cut set here. So we need to figure out what's common between the available expressions on the left-hand and the right-hand side here. And of course, x plus 5 is only available on the left-hand side here. Y minus 7 is only available on the right-hand side here. So only x times y is actually available in both passes leading to our instruction down here. So we can make sure and we can be sure that x times y is available here. Of course, we're killing it right away. So yes, we can't optimize a lot in this very simple example here. So from this we can derive our data flow equations again. So our data flow equations tell us everything we need to know to implement this information. So how do we propagate availability information throughout our program, throughout our control flow graph? So the unavailable variables for a program point n is the join, now the cut of all the out available variables of all the predecessors of our program point, and on the other hand, the out available expressions of a program point n is, as we've seen, the unavailable expressions joined with the one we generated, and we subtract the ones we kill in our instruction n from that. And you see the one is expressed in terms of the other, so we can put that one here, or we can put that one here. So we can combine both to create an overall availability equation. So available expressions at a node n is the cut set of all the predecessors of a node n of the available at that predecessor joined with the ones generated in our current instruction minus the ones killed in our instruction. So we can use this here to define our set of equations here, and the important thing is that we use this cut operator to capture the nature of data flow, that we need to know that all paths are actually considered, and this is different to liveness and reaching definitions analysis we've seen before, and the direction of data flow is forward like in the reaching definition, whereas in liveness analysis it was backward. And what can we use this for? Now, one thing we can use this for is common sub-expression elimination. So this is an optimization that searches for instances of identical expressions, so expressions that all evaluate to the same value. And this optimization analyzes whether it's worthwhile to replace the instances with a single variable that holds the computed value. So for example, if we have these two expressions here, a equals b times c plus g, and d equals b times c times e, we see, well, b times c is calculated twice here, so maybe we could transform it to something like calculate b times c only once, store it in an intermediate variable, and then use this intermediate variable instead of the original expression to calculate a and d. So that was a quick overview of our static analysis here. And in the next lecture, we'll have a final look at the last static simple analysis, and we'll conclude this. And after that, we'll continue on with more things in the compiler backend. Thanks for listening. Until next time.